Okay, so we had spoken about the differentiability issues, because ultimately in optimization differentiability is what matters in a major way. So we found that every critical point, that is any point where grad f(x) bar is equal to 0 is a global minimum, and even if it is not so, if you do not bother about differentiability of the function, every local minimum is global. So this is the basic idea that we have studied so far and giving examples of convex functions. So in your exercise, which a thing that you have to, my students would also help you, is that when do you know that a given function is convex? So that is very important. Okay, if some functions are already known to be convex, you know it, then it's all right. But given a function, how do you know it's convex? In fact, one of the major ways to learn the convexity of a function is the following. So if a function is twice continuously differentiable, that is, if its Hessian matrix exists and is also continuous, if f, so that is given by, say, in this notation C to say Rn, twice continuously differentiable, then f is convex if and only if the Hessian matrix of f at x is positive semi-definite for all x. There are several other versions of convex functions which we have not introduced, but we will just give you while in the exercise. So now we come to this core issue of handling non-differentiability, because as we have given this idea that and showed through examples that convex functions are not only non-differentiable almost everywhere, differentiable almost everywhere, non-differentiable at a few points, but they are non-differentiable particularly at points where the problem has a minimizer. So one important definition is that of a directional derivative. Directional derivative is something that you learn in vector calculus, that if you have a function f, say from Rn to R, then the vector derivative simply means, no, it's too small. Keep it back. The directional derivative means given a point x, I can move along a given direction, say h, and I'll record the change of the function along this direction, and that is what is the meaning of directional derivative. So I'll look at the derivative along a ray. So basically, in a situation where I am in multi dimensions, more than one dimension, I am bringing it into a single dimension. That is the idea. So that is the way it is defined, that the directional derivative of f at the direction h, this symbol lambda down arrow 0 means lambda is positive and going to 0, because for convex functions only one sided directional derivative would exist. We cannot talk about lambda up arrow, means lambda is negative and going to 0. So this is the definition, and if the function itself is differentiable, that is has a gradient vector, then this is the standard relationship that you know from vector calculus. You can check it up in the net if you want, this relationship. But because the interesting part of convex functions is that even though this thing does not exist, when the gradient does not exist at a point x say, we can still talk about the directional derivative. It does not need to fit into that relationship, but still we can. So, now the question is, when does it exist finitely? Of course, over the given domain, if you take any x in the domain of the function f, right, then it will always exist even if you allow infinite plus infinity value. And the interesting part of this is that as a function of, so if I fix an x and keep on changing my h, as a function of h, it is a positively homogeneous convex function. Positively homogeneous means that it satisfies this property, that f dash x of lambda h is equal to lambda f dash x h, where lambda is greater than or equal to 0. This property is called positive homogeneity. So, it is a positive. So, the important part is that the directional derivative in the direction for a given x is a positively homogeneous convex function. So, convex functions can take plus infinity minus infinity values, right. So, if you allow infinite plus infinity minus infinity values, then for any x element of domain f, this function exists at a given x in any direction you want. But if you want it to exist finitely, then you have to be bothered with certain issues. Then the issue comes that the domain f of the domain of the convex function must have an interior. When the affine hull has to be exactly Rn, and for any x element of the interior, you will have that the directional derivative exists finitely. So, if you take a function from Rn to R, then at every point of Rn, the directional derivative exists finitely, even if you do not have the derivative. For example, if you want to calculate, so you take this function f x is equal to the modulus of x, x in real line. So, you want to calculate this f dash at 0. So, 0 you do not have the derivatives, 0 h is limit lambda tends to 0, 0 plus lambda h. So, it will become lambda h minus at 0 it is 0 lambda h by lambda. So, lambda is positive. So, it will become limit of lambda tends to 0, because lambda will come out of here, because lambda is mod lambda will come out of here, but lambda is positive. So, it will cancel with this. So, so it is mod h. The directional derivative of the function, see directionally given a fixed x, the directional derivative is a function of this direction h. You change the directional derivative value will change. X is fixed. See, the problem is that in such cases you do not, in optimization you do not really require to change both of them simultaneously. If you change both of them simultaneously, then it is a very not a very interesting thing. But what happens is that if you have that this exists, then this will exist in a finite way. This will be finite, that if you are taking elements from the interior of domain, then this is a finite valued on a finite number, and fixing the x, whatever h you take, if x is in int of domain, whatever h you take, then that class of convex functions, that convex function is a finite positively homogeneous convex function. Okay. So, let us take another view, because you have already we had already spoke about supporting hyperplanes yesterday, that if you have a closed convex set, you can draw a tangent line or a tangent plane which is touching at the boundary and passing through a point in the boundary. So, these are supporting hyperplanes. So, if you look at where is the So, I am not rubbing this, I am keeping it for the exercise in the next class. So, if you look at this, so again you go back to the prototypical example, f x is equal to absolute value of x, and you look at the epigraph. So, the epigraph of f is a closed convex set. In fact, it is a closed convex cone. It is a polyhedral cone actually, if you want to. And this at this point x equal to 0. So, I try to draw a supporting hyperplane. You see, all the supporting hyperplanes that I draw at x bar equal to 0 would lie below the graph. Now, this point does not have a derivative. So, the slope of the tangent, but slope of any of the supporting hyperplanes, lines basically, can be considered as a candidate for being a gradient. So, each of these are called a subgradient, because they are really not gradients, because gradient means there is only one. So, this is the it is a subgradient, and so the slope of each of these. So, the slope varies from +1, which is this line, to -1. So, all the elements from -1 to +1 can be thought of as a candidate for gradient at x bar equal to 0. So, now we move to a different paradigm, where instead of just taking a vector as a gradient, we will view the gradient as a set. So, this set is called the set of subdifferentials, which we write like this. The set of subdifferential of the convex function f x equal to mod x at x equal to 0 is this. Now, what is the plus point of this? Now, you know, at the point where you have a minimizer, here 0 is the minimizer, you know the very basic rule in optimization, that the derivative or the gradient must be equal to 0 at that point. That is a basic necessary condition. Here, you see at x bar equal to 0, you do not have the gradient, you have what is called a subdifferential, but you always have this fact, 0 element of you have this fact. So, the necessary condition for optimality, the Fermat's rule, is captured here, and that is the key fact, that you have captured the Fermat's rule, and as a result of which you can think this object as a real good way to replace the gradient here. Of course, questions would come, especially from numerical analysts, that why can't I do certain approximations, like I do certain finite differencing, central differencing around the point x bar equal to 0, and try to find an approximation of the derivative. If you do central differencing, the answer of the derivative that will come at x bar equal to 0 would be half. But half does not capture the real fact that x bar equal to 0 is a point of minimizing point. So, the gradient must be 0. Whatever you do at that point, that the fact that it has is a minimizer, that intrinsic property of the point x bar equal to 0 is that it is a minimizing point, and that has to capture, the math has to capture that fact. But if you do central differencing, the math will not capture that fact, it will give you the answer half. So, there is a famous statement by Claude Lemarechal, who is one of the famous guys in algorithms for convex optimization. He says that mere finite differencing in non-smooth optimization is a sin against mathematics. So, you really have to, and if you want to go and do something like called distributional derivatives, I do not want to get into all this, then you really have to forget about this point. So, this is so the only way we can capture, that is where the convexity, the power of convexity, the separating hyperplane, all these things comes into play. That this separating hyperplane idea actually captures this real fact, 0 element of del f0. That is, at the minimizing point, 0 must be an element of that set. So, let us give a very candid definition of a subgradient. So, of the subdifferential. So, let us consider a proper convex function, Let us consider x bar element of the dome of f, right. Then the subdifferential of f at the point x bar is a collection of all v, a collection of all vectors v which satisfy this condition. So, it is a collection of all vectors v which satisfy this condition. You have seen in the last class, or not, sorry, in the morning class, means last class only, that we had written a formula like this. Every differentiable function is convex if and only if this is true for every pair x y. Geometrically, what does this capture? So, I can rewrite this as so, geometrically, what does it capture? It captures the following fact that if you take a convex function, say this is your point x, draw the tangent line at this point. The tangent line, equation of the tangent line is given by this, y equal to f x plus this, because you just calculate the slope. Because I am just talking about here in one dimensional case, it will become the derivative, right. So, what you will do here is, so this is your y, so this is your y, and this is your f y. So, what is the tangent line? Tangent line is that y hat, the tangent line. So, on the tangent line, this is say, or I write as z hat, is nothing but what? Or just write the slope of this tangent line. Slope of the tangent line is what? It will be this y hat. So, y, suppose this is y z. So, it will be z minus f of x y minus x, and this is equal to f dash x, the slope, because derivative is nothing but the slope of the tangent. So, what do I get from here? I simply get the following from here. This would simply imply that z minus f x is equal to f dash x into y minus x, showing me that z is equal to f x plus f dash x into y minus x. But you observe the z is here. So, this is z, but this is your f of y. So, f of y is actually bigger than z. So, which means that f of y, from here you will simply get that f of y is greater than equal to f x plus f dash x into y minus x. That idea in a higher dimension is given by this, because now because the derivative would be replaced by the gradient, and the gradient and the multiplication would be replaced by the inner product. And if x is not in the domain of f, then this is defined as an empty set. Now, what I want to talk to you is the following, that now, if I want to define a subgradient, why is this definition? If you look at this thing, whatever be the slope of the tangent, if you write down the equation of the tangent line exactly in the same way what we did here. So, you take any supporting hyperplane here and assume that the slope of that line is v, then you will similarly you get this expression. But there are not only one tangent line, there are many tangent lines. For all of those v's, this will be true. So, collection of all those slopes of those tangent lines is actually the subdifferential. So, let us show any other example. There is now is this the only way to compute the subdifferential? Have you really have to go through checking such inequalities, which might be a very difficult task. But here we will use the fact that a convex function is actually differentiable almost everywhere. This is the fact that we will use, and so let us look at the property of the subdifferential set. So at a given x bar, in general del f x bar is closed and convex. But if x bar is in the interior of f, then del f x bar is closed, convex and bounded, that is convex and compact. So here, so there is a small error that you have to put in. Here you have to write if x bar in this place, if x bar is in the interior of dome f. So those who are attending this class for the first time might get little bit of a problem, because I am using terminology which I have already introduced in the morning class. So you see that for example, if you look at this convex set, convex function, that is f x equal to 0, we had discussed this function in the morning. If x is equal to 0 and plus infinity is x is not equal to 0, it is actually the indicator function of the singleton set 0. Now, basically what is the subdifferential of this? Subdifferential is the whole of R, because there is an interesting fact that the subdifferential, if you look at the subdifferential of an indicator function is actually the normal cone, which we had introduced in the last class. That is the subdifferential del of f x, the subdifferential of the indicator function is the normal cone to C at x. So if you draw the normal cone, you will really realize that this is nothing but the whole of R. So unless unless the dome f, here the dome f is just this point. So this point, a singleton set does not have an interior, but it has a relative interior by assuming that its affine hull. Its affine hull is itself, right? That is it. So now another way of finding the subdifferential. This is the most practical way to find out, compute subdifferentials at various points. See, what happens is the following: a convex function. So given a plane, say Rn or R2, the convex function is not differentiable only at few points, and it is differentiable everywhere else. So given a point, I can always find a sequence of points at which the convex function is differentiable, and then it comes and converges to this point. So you can find many paths coming and converging to that point. So you move along those paths. So at those points xk's, where xk is a set of differentiability points, you compute the grad of fxk. So take one sequence, calculate the grad of fxk, and take a limit. So you keep it in one box. Similarly, you take another xk, because you are in Rn or say R2, there are not only just two paths, there are many paths. We will show an example in R, so you will see just two paths. I can put an example in R2 also, but it does not matter. So there are many, many paths. So you take any xk sequence which converges to this x bar, at each point xk, you take the derivative, and then you take the limit as k tends to infinity, and you collect all those limit points, and then you make them take the convex hull of that limit point, make it into a convex set. and what you get is exactly the subdifferential of f at x bar. For example, consider this function. As I told you in the morning that the maximum is actually introduced, the maximum function is actually introduced here as a very important idea, because as I told you, the non-smoothness in convex functions arise because you take a operation of maximum. It just does not arise from the blue. There is always a operation of maximum at the back if you want to, if you are generating non-differentiable convex functions. So, this is the key function that one needs to study actually. So, if we look at this problem, so it is max of x square and x. You understand that here x, so this is y equal to x, this is the line, this spot, and this is the graph of x square. Okay, the graph is not, doesn't look that good, but this is a graph of x square. Now, when you are coming from the negative side towards 0, x square is non-negative, but x is negative. So, x square is the maximum part, it will give you the maximum value of among the two, that will be the higher one. So, the graph is here. But when you come in the positive part, between 0 and 1, x is always bigger than x square. So, then you just take this part, and then after 1, x square is again bigger than x, so it goes up. So, here you have a straight path, here you have a, so you have non-differentiable points. So, the point of non-differentiability is x equal to 0 and x equal to 1. All right, the points of non-differentiability are x equal to 0 and x equal to 1. Now, let me try to calculate the non-differentiability point, right, at the subdifferential at 0, because the derivative does not exist here, because in this side the derivative value is 1 and this side the derivative value is 2x at every point, and you come to 0, it will be 0. So, if you take the derivative along a sequence coming from this side, the derivative is 2x, derivative x square, and as x tends to 0, it becomes 0, and from here the derivative is only 1. So, ultimately as x tends to xk tends to 0, what will you get? The limit value would be 1, because you can say I can come here, the limit value is, but you do not need this side, because convergence ultimately means what happens at the tail of the sequence, it does not bother about what happens at the head of the sequence. So, basically now you take the convex hull of that point 0 and 1, so you get this closed interval 0 1. So, this is my subdifferential at 0. You see 0 is again at this point, because 0 is a minimizer. In fact, for a convex function, x bar is a global minimizer of a convex function f over R, and if and only if 0 is a subdifferential. Now, look at 1, this point 1 is not a minimizer, because the functional values are lower than 1 at this point and higher than 1 on this side. Then it must be necessary that 0 cannot belong to this set, because once 0 belong to that set, that point must be a minimizer, because of the definition, you know, just this is same as what we did in the morning class, that if you have zeros, that is if you have fy minus fx, so x is the, so this v actually now belongs to the subdifferential of f at x. Assume that this holds for all y. Now, what happens? If I put 0 here, then for every y, fy would be bigger than fx. So, if 0 is element of the subdifferential of f at x, then x is a global minimizer, and if x is a global minimizer, then 0 must be in the subdifferential. Because if it is, if x bar is x is a global minimizer, then fy is greater than equal to fx for any other y. So, fy minus fx is greater than equal to 0. So, if I put v as 0, 0 into y minus x is 0. So, the 0 thing 0 v equal to 0 actually satisfies that inequality, that is it. So, 0 is a minimizer. Now, you see, look at this point x equal to 1. So, if I come from the left side, my limit value is 1 because the derivative is 1. But if I come from this side, at every point the derivative value is 2x because I am differentiating x square, and then as I go towards 1 the limit is 2. So, the convex hull of this 1 2 points 1 2. So, if you just have 2 points 1 and 2. So, what is the smallest convex set containing this? This, because it is nothing but the line segment joining 1 and 2. Given 2 points, the smallest convex set containing that would be nothing but the line segment joining those 2 points. So, what is del f1? It is 1 2. You see how beautifully the math is capturing the nature of the point. The point 1 is not a minimizer, so 0 does not belong to the subdifferential at 1. At the point 1, the subdifferential set is free of 0. So, here is a very big paradigm shift, and you are absolutely at the frontier of knowledge, because here we are making a huge change. We are telling that the derivative, which is a vector, which is much more easy to handle, is now being replaced by a set. At every point, instead of calculating the derivative, we are calculating the set. In fact, I will give you as an exercise the following, which we will write after the end of this class, that if a convex function is differentiable at a given point x bar, then the subdifferential contains nothing but the singleton set x bar. So, at the points of differentiability, the subdifferential set reduces to the singleton set containing only the gradient at that point. So, you see it is very natural. So, subdifferential can be thought of as a natural extension of the idea of derivative for a convex function. So, here is what we had, you can also figure out why the subdifferential of this is NCX. I would ask you to figure this out. So, that would be another exercise. Because I have a departmental meeting, which is the unfortunate thing we all have to face. Even with the request of having this course running, I was not freed of it. Emergency meeting, it seems. So, you would understand. So, I will ask my whatever I am telling as exercises, my PhD students will write it down on the board, but I will come back after half an hour and we will actually go through the exercise. Now, this is a property which we have just discussed, that if 0 is an element of the subdifferential, then if x bar is a minimizer of f over Rn, assuming that function is from Rn to R for the moment. Of course, this holds even if you take Rn to R union infinity, because if x bar is a minimizing point, f x bar cannot have plus infinity value, then it is not a minimizer, right. So, if this property actually holds if x bar is a minimizing point, right. Of course, at the minimizing point it must have a subdifferential. If it does not have a subdifferential, then there is an issue. And the subdifferential has to be non-empty. The subdifferential is always non-empty for a point x bar in the interior of the domain. It is always non-empty, convex and compact. But it can cause, there can be a cause of problem at the boundary, right. So, there is the issue of lower semi-continuity of convex functions and all, which we are not going, because that needs a very different sort of training to actually go through that. Now, the subdifferential has a very interesting link with the directional derivative that we had already mentioned. So, what we had said that if the function is differentiable, then the directional derivative in the direction h is nothing but the inner product or dot product between the gradient and the direction. But in the convex case, how does the directional derivative is linked with the subdifferential, because subdifferential is now playing the role of the gradient. So, you see that the paradigm shift, instead of a vector, you have a set. Instead of a standard inequality grad f x bar equal to 0 for minimization, you have a set, you have 0 element of del f x bar. So, your equality is changed to an inclusion, and that's the paradigm shift. So, here f is from Rn to R, we just take the basic situation for you, and then this is the relation between the directional derivative and the two-step relationship. One where the subdifferential is expressed in terms of directional derivative, another where the directional derivative is expressed as a kind of linearization of the subdifferential itself. So, the directional derivative is actually v of h. So, if it just contained the gradient, if at x bar f was differentiable, v was nothing but grad f x bar. It would have only one thing, then this would be nothing but equal to grad f x bar h. You will get back the thing that you already know. So, this is a very beautiful result. It actually generalizes that result for vector analysis to that for convex analysis. So, this is a very, very important result that one has to remember. It is a very useful one. I think John will also use something like this sort of results. Now, we come to what is called calculus rule for subdifferentials. See, I will be speaking mostly on convex functions because John will also speak mostly on convex functions. There will be some non-convexity someplace, but largely it will be convex and linear. So, linear functions are also special class of convex functions. I have not written in the examples linear functions. I assume that linear functions would you would understand that linear functions are convex functions. In fact, linear functions are a special class of functions called affine functions, and just in the tutorial class explain to them what an affine function is. Now, because I am claiming that the subdifferential set is a substitute for the derivative of a convex function, then I must be able to say that okay, now I should be able to demonstrate to you that it has behavior like the derivative. So, one of the primary behavior of the derivative is that the derivative of the sum of two functions is the sum of the individual derivatives. So, the derivative of the sum of two functions is the sum of the individual derivatives. So, as you know that here we are in a much more technically higher ground, and you have that if f1 and f2 are proper convex function and the relative interior of their domains do not have a non-empty interior, a non-empty intersection, then this is a result due to Rockefeller. Then for every x in the intersection of dome f1 and dome f2, you see, because we are adding a function f1 and f2 at the point x bar on which we apply, which we want to apply the function f1 and f2, because has to be from this point, because you see f1 plus f2 this is defined as f1 x bar plus f2 x bar, means at x bar the function f2 must be defined and be finite, and f1 x bar must be also defined and finite. So, x bar must be in the domain of f2, x bar must be in the domain of f1, and hence it must be in the intersection. So, this is the famous sum rule, this is called the sum rule. See, in general the following thing is valid. In general it is valid that, so del of x1, del f1x plus del f2x is a subset of del f1 plus f2x. This can be proved very easily applying the definition of the subdifferential. You try it out in the, let them try out in the class. So, but to go do the reverse thing to show that this is a subdifferential, this is a subset of this is a difficult job. It needs certain more separation theorems and all those things. So, here is the scalability of a convex function. So, if I scale a convex function by a lambda greater than or equal to 0, then the subdifferential of lambda f is nothing but lambda of the subdifferential of f at a given point. One has to observe that lambda of f is a convex function only when lambda is greater than or equal to 0. If lambda is negative, it is not a convex function. If I put lambda equal to -1, it becomes a concave function, which we had discussed. For a concave function, the property is opposite. The property is that every local maximizer is global. And that is why concave functions are important in economics, where you are seeking maximization. And convex functions are important in engineering, because you are seeking minimization. So that's the whole idea. Economy seeks to maximize profit. Engineer seeks to minimize cost. So there are two different paradigms, but they are all basically essentially the similar kind of problems. So see these classes, now you can say, okay, what is the big deal? Okay, this is just what we know for derivative, or sum of if you have addition of derivative of the addition of two functions is the addition of the individual derivatives. Oh, you have done this by del f1, but here remember, this equality is not an easy equality, it is the equality between two sets. And this del f1 x bar and del f2 x bar, this addition is the Minkowski addition of two convex sets, which we had discussed in the last class, in a class of convex sets. That is what it is there. So that has to be kept in mind. Now, one important thing that we should focus on is that what makes this convex analysis different from the standard differential calculus. What makes convex calculus different? The difference is that you can compute the subdifferential of a max function, because the max function is in general not differentiable even if all these are differentiable. The max function is not differentiable even if all these are differentiable. Okay? Even if all these are differentiable, the max function is not differentiable. So you cannot compute the derivative of the grad of fx. You cannot compute the derivative, or you cannot compute the grad of f of x. For a max function, you cannot, there is no derivative in general. So the differential calculus games won't work here. So you really have to, so here is a concrete example of a convex function which is non-differentiable. So but techniques of derivative won't work there. Here is how you calculate the subdifferential. That the subdifferential of x is convex all of these. You take the gradient of all these, where j belongs to jx bar. So jx bar is a collection of all indices for which f of x bar is fjx bar. So when you compute f of x bar, so you are computing f1 x bar, f2 x bar, dot dot at fm x bar, and from them taking what is the maximum value. So there can be two, say f1 x bar and f2 x bar, both can be equal to, both can have the same value and the highest value. So those are precisely the points where non-differentiability creeps in. So and then both of them equal to the function value. See what happens if jx bar is such that there are more than one index as j for which this happens, then that is exactly those are non-differentiable points. But if x bar is such that there is only one index, then it is not a non-differentiable point. So this is a very important thing to remember, that in this jx bar or the active index set, so here j is the index, I 1 to m basically. So such that this happens. So if there are more than, suppose the index 1 and index 3 is there such that this happens. So fx bar is f1, fx bar is f2 equal to f2, f3. Then at such a point the function is non-differentiable. So largely for most cases jx bar would be just singleton, and then, but there are few points at which jx bar won't be singleton, at which the subdifferential needs to be calculated. Okay. So this, what is the ramification of this rule? So this is a formula that makes convex analysis special. The ramification of the rule is that now if I am given a concrete convex optimization problem that minimize a function subject to certain inequality constraints, I can actually use this rule to derive the Karush-Kuntaker conditions, the famous KKT conditions in convex programming. And that is exactly what I am going to do. And then I will come to the very basic general formula for convex optimization problems, and with that we will end the talk. So, let me do this. Okay, so I'll just rub this up also. Poonam, just rewrite this exercise and help them do this. So here I am given a very basic mathematical programming problem. Minimize fx subject to here my feasible set consists of, so this function f is assumed to be convex, and this is also assumed to be convex over a common domain. Let us assume that all the f and gi's are convex functions from Rn to R, just for simplicity of the writing. You can increase the technical level, there is no problem. So we are assuming that f and gi's are functions from Rn to R and differentiable, convex of course and differentiable plus convex. My question is, can I find a condition which will be both necessary and sufficient for the existence of an optimal solution of this problem? First step is a necessary condition, because that would allow me to calculate a candidate for a maximum minimum, right? And if you can show that particular condition is sufficient, then it is very good. Just by solving that condition, you can actually get the solution. See, this subject is too vast, means you cannot really in one lecture talk too much about it. So then it will need a whole Gyan course to do this subject itself. So because you are more into stochastic things, but these will be used. So you just know the tools, right? So just to enthuse you, I tell this story often to my students in my class when they get too bogged up that, okay, I am not getting the proof of this and I need a proof. But sometimes you have no other choice not to give the proof because you are doing something else. So I will tell there is this famous story about John von Neumann. There was a student in Princeton who was doing his PhD in physics. It's a true story actually. So he got stuck up in some PDE and his thesis supervisor couldn't do anything to help him. So he said, okay, why don't you go and catch Professor von Neumann? So he couldn't get an appointment with von Neumann, who was in the Princeton Institute for Advanced Studies. So he said, then his supervisor said, okay, when he comes to the dance floor at night, so you just go and talk to him. So he found Professor von Neumann at the dance floor dancing with a nice lady, and he comes and tells that, okay, can you tell me this is the problem, how to solve it? He said, use the method of characteristics. So he goes back, finds out what is the method of characteristics, applies that and solves his problem. So he was very pleased. So he calls up von Neumann in his house early in the morning and says, Professor von Neumann, I am very pleased that the method you have said actually had solved my problem. But I really don't understand what is this method of characteristics. And von Neumann said that, my son, you don't understand things in mathematics, you just get used to them. So I am just telling you to get used to these things, because then only you can pull through the course. Now, suppose x naught is a minimizer, is given to me, minimizer of this problem. So let me call it CP to say it is a convex programming problem, minimizer of CP. Then one can show, then equivalently means, or maybe just I don't want to write it, then one can show that x naught is a minimizer of the function, means unconstant minimizer. Here minimizer simply means global minimizer, there is no local minimizer in the convex case. Minimizer of the function observe that minimizer of the function capital Fx, which is given as max of Fx minus Fx0. So, if we add a constant to a convex function, it remains constant. Now, you see why I am calling it a convex optimization problem, because if I look at the feasible set of this problem, and the set of all x in Rn such that gix less than equal to 0, applying the fact that all of these functions are convex, you can show that this is a convex set. Put this also as one of the exercise, just for them to check that this is a convex set. That is they learn how to use the convexity inequality. And so now, if x naught is a minimizer of this problem, then x naught is a minimizer of this convex function. Now, consider a set Ix bar, it is called a set of active indices. A set of all I element of 1 to m such that Gix bar is equal to 0. You will see why this is. Just for the moment, let just take that this set is being used. We will see why this is important. Now, if x naught is also a minimizer of this function, so I know that the optimality condition is 0 element of the del of f at x naught. Now, what is j of x naught? So, find the indexes which are in this set. So, j of x naught means either it has to be this index, indexes are from here now. Now, you see when x is equal to x naught, this is 0. Now, among the g1x, gmx, there are some x for which some indices for which gx naught is equal to, sorry, not gx bar, sorry. So, there could be some i's for which gix naught is 0, and for all the other i's, because x naught is a feasible point, because it is a minimizer, it must be feasible to the problem, otherwise there is no use of being a minimizer. The minimizer must also satisfy this inequality. So, gix naught is either strictly less than 0 or it is equal to 0. But you see, if all of these are strictly less than 0, does not matter, f of x naught is always equal to 0, because this is 0, because once I put x equal to x naught, this is 0. So, now among these things, there might be some of them where gix naught is 0. So, those will also become a part of this jx bar, jx naught index. So, if I call this index as the 0 index, then it will have the 0 index union ix bar, ix naught. Ix naught is the set of points, set of indices for which gix naught is 0. That will constitute your jx naught. So, which means now by the very definition, del fx naught is the convex hull of grad of fj x bar, sorry, fj x naught, and wait, I will write it in a better way. So, del of fx naught is equal to the convex hull of all grad f j x bar which are in this j x naught. So, it will be grad f j x naught. So, this set union grad g I x naught where I is element of I x naught, because these are the indexes in that set. So, we are exactly applying this formula. So, what is the meaning of convex hull now? So, there would exist lambda naught, lambda 1, lambda 2, lambda m where I is in I x naught such that 0 must be. So, by this formula we have 0 belonging to this and this is nothing but this. So, because I want, so 0 must be element of the convex hull of this. So, there must exist lambda naught greater than equal to 0, lambda I greater than equal to 0 for all I element of I x naught such that lambda naught plus summation lambda I is equal to 1 to, sorry, I belongs to I x naught is equal to 1, this plus and also you will have 0 must be equal to lambda naught of grad f x naught plus summation lambda I of grad g I x naught, I belongs to I x naught. So, now I can make this look a slightly bit better by assuming that whenever I is not in I x naught, that is whenever I is not an active index, that is where g I x bar, g I x naught is strictly less than 0, I will say that lambda I is equal to 0 at that point. So, I am just rubbing this up. So, if we set lambda I is equal to 0 when g I x is strictly, g I x naught is strictly less than 0, then we can write the following: lambda naught grad f x naught plus summation lambda I grad g I x naught. So, now I can run the index. See, this I x naught is very difficult to know which are the indexes, right. So, it is a very clumsy way of writing. Now, I am writing from I equal to 1 to m, but because of this property, what does it mean? That whenever g I x naught is strictly less than 0, lambda I is equal to 0. Whenever g I x bar is equal to 0, lambda I could be strictly bigger than 0, could be equal to 0, does not matter. So, the second condition, which is a combination of this fact and the fact and also the active index things, it is the following, that lambda I g I x naught is equal to 0 for all I. That is, both lambda I and g I x naught cannot hold with strict inequalities at the same time. If one of them is strict, the other must be 0. If lambda I is 0 strict, then g I x bar must be 0. So, whenever I is in the active constant set, then and then only can lambda I be possibly strictly greater than 0. So, the Lagrangian multipliers lambda I here can only be strictly bigger than 0. This is called Lagrangian multipliers. I am using the term because I am sure in calculus you have learned the very basic Lagrange theorem, that you have f x and g x, and if you write f plus lambda g, take the gradient. So, okay. So, these multipliers that you see, but you see, where are the multipliers coming from? Multipliers are coming while you are trying to take a convex hull. So, multipliers are arising out of a geometric construction. So, here multipliers are linked with the geometry of a convex set. That is the beauty. This is the beauty of mathematics. Usually economists would try to talk about multipliers in terms of shadow prices, but here we can talk about multipliers in terms of a geometry of a set. Now, you observe that here there is a little problem that lambda naught could be equal to 0 and then grad f x naught would not take part in the optimization process. So, how can we make lambda naught strictly bigger than 0? How can we make lambda naught strictly bigger than 0? That is the question. This can be achieved, and this is also an exercise. I think the last exercise would be this, that if there exists x hat such that gi x hat is strictly less than 0 for all I equal to 1 to m, then I can show that lambda naught here can never be 0. So, whenever it is not equal to 0, I can divide both sides by lambda 1, because this is equal to 0, sorry. So, this is equal to 0 from here. So, I can, if I lambda naught is strictly bigger than 0, then lambda naught, we can divide lambda naught by this side. This equation can be divided on both sides by lambda naught to get an expression of this form. And this is the standard expression that you know in the Lagrange multipliers rule. So, lambda I by lambda naught I can put as lambda naught, lambda bar, say lambda bar I. So, this becomes equal to 0. So, if to prove that lambda naught equal to 0, we have to assume this condition which is called the Slater condition. So, I would ask one of my PhD students to demonstrate why this is true. That if you have the Slater condition holding, then the Fritz John condition would actually give you the Kuhn-Tucker condition, that lambda naught would be strictly bigger than 0. One of the greatest plus points once you have this, then once lambda naught is greater than or equal to 0 and you write it in this form, then this condition and this condition, this constitutes what is called the famous Karush-Kuhn-Tucker conditions for a convex optimization problem. But the beauty of this condition is that if there is an x naught which is feasible to the original problem and there is a lambda I bar with respect to which these two conditions are satisfied, then x naught is actually a global optimal solution of the convex programming problem. So, it is a if and only if condition, and that is where convexity draws all its powers from. So, these two problems, that Slater condition as well as the fact that KKT conditions are also sufficient in a convex case, because we are only dealing with convexity here, has to be told as an exercise. And please, I think that will be a slightly bigger exercise, just demonstrate them. I will come back after half an hour and then we can demonstrate that. Now, what I want to show is a very general result in convex optimization that so, if you are having a very general system, f is from Rn to R, you can also take R in infinity, so the technicality would increase, and C is a subset of Rn, closed and convex. Then write down an optimality condition for this, which is both necessary and sufficient. So, the idea here you see we will make use of the indicator function. So, if I minimize this function f over the convex set C, it is same as minimizing the function f plus del Cx over Rn. You see, whenever I have given the indicator function acts as a penalty. That is, if you are out of C, you pay infinite penalty. So, you are forced to remain inside the feasible set. So, if you are inside the feasible set, del Cx bar is 0, so there is no penalty. So, these two problems are equivalent, which you can easily show, but maybe you should try a bit at when you are off. Now, then, so whenever x bar is a minimizer of this, x bar is a minimizer of this. So, this implies that 0 is element of this, the element of the subdifferential of f plus del C. Now, you apply the subdifferential sum rule. So, what is the domain of f? Domain of f is Rn, and the relative interior of the domain of f is Rn itself, because Rn is open set, it has an interior. C is a convex set. So, relative interior of the convex set C is non-empty. So, Rn intersection the relative interior of the convex set C, is that empty or not, or non-empty? So, what is this? So, here see what I am trying to say is that I have to apply the sum rule here, because it is sum of two convex functions. All of the both are proper convex functions. So, in this case you see dome of F is Rn and dome of del C is C. So, when can I apply the sum rule? If the relative interior of dome F intersection the relative interior of dome C is not equal to phi, right? Then only then I can apply the sum rule. So, what is the relative interior of Rn? Relative interior of Rn is equal to the same as the interior of Rn is equal to Rn itself. So, what is now relative interior of C is of course there, it is not empty. No. Now, Rn intersection relative interior of C. Now, C is a subset of Rn. So, relative interior of C is a subset of Rn. So, Rn is a superset. So, this is nothing but A intersection B. If A is a superset, what is A intersection B? B itself. So, that is exactly. And this is non-empty, which we already know, because every convex set C has a non-empty relative interior. And so, this intersection is non-empty, and hence we can apply the sum rule, which is 0 element of del fx bar plus the subdifferential of the indicator function. But we have shown that the subdifferential of the indicator function is the normal cone. And this is called the Rockefeller-Shenichny condition. A huge amount of mathematics, a huge amount of optimization, when you go beyond convexity, is actually trying to compute a very general version of this normal cone. And because Lagrangian multipliers are lying hidden here, when C is expressed as this, the question would be, how do you compute the Lagrange multiplier rule? Now, how do you compute this NCX bar? So, when C is this, if C is this, the question is, what is NCX? How do you compute this? And that's not an easy thing. That's not a straightforward thing. So, with this, I will actually stop my discussion of convex analysis and optimization. So, Professor Borge will take over from the next day, and I will I'll ask him. I thought of speaking a bit about numerical things, but I think maybe it would be better to leave it to him to decide whether he would like to talk about numerics, because he would finally talk about the numerics in stochastic. So, if he can give some idea of numerics here, or we can both jointly do it. So that's the end of today's discussion. At 4 we'll start the tutorial.